Hi guys, welcome back to Data Every Day. Today we're looking at a gender recognition by voice dataset. This is really the task. The dataset is they're records from different people, and these are statistics about vocal ranges, and it's basically vocal data. You can see we have a lot of like means, mins, maxes, ranges. It says here, this database was created to identify a voice as male or female based upon acoustic properties of the voice and speech. So it actually comes from recorded voice samples, which were then analyzed, and these features were created from them. So let's get into the notebook. What I'm going to try to do is, as it would like us to do, try to predict the gender of a given person based on these vocal features. And we're going to use, I wrote two different neural networks, one a CNN, and this is mainly just for fun. What we're going to do is we're first going to just use a traditional two hidden layer neural network, and then we're going to try something else. We're going to restructure the data into like two-dimensional images, and we're going to try to use a convolutional neural network on that. Alright, so let's get started. I have NumPy, Pandas, and Matplotlib, the essentials. Then I have, for pre-processing, label encoder, standard scaler, and the train test split function from sklearn. And then I have TensorFlow, which I'm also going to use a number of functions from Keras module TensorFlow. Alright, let's load in the data using pandas.readcsv. And we can get the file path up here, voice.csv. Let's copy that, paste it in, and take a look. And you notice first thing is that we can't see all the columns, so I'm going to go into the console and write pandas.setOption max columns none. And that will give us all of the columns. And you can see they're already in numerical form because these features were created from voice samples. And we just noticed that the label column needs to be encoded. Before we go any further, we should check if we have any missing values, although I doubt we will. Yeah, no missing values. 3,100 entries, and you can see there's no nulls in any of the columns. Alright, let's encode the labels. So I'm just going to use sklearn's a label encoder for this, which we just create a new object, and then the column we want to encode is called label. So data sub label equals label encoder dot fit transform data sub label, and that will just change it so that male and female are assigned 0 or 1. And we'll run that, and we can actually take a look at which values were mapped to which by enumerating label encoder dot classes underscore. And when we enumerate it, we can then turn it into a dictionary to get a mapping of what went to which. And you can see 0 went to female, 1 went to male. Other way around, female went to 0, male went to 1. So you can see if we were to look at the data now, we have 1s and 0s, whereas before we had male and female. Okay, let's split and scale the data. So we're going to split it into X and Y. Y is what we're trying to predict, just our label column, data sub label, and I'll make a deep copy of it. And X is going to be everything except label. So we're going to drop it from axis 1, make a copy of that, and now we have split our data into two sections. Y is just a vector, X is a matrix. And let's create a scalar. Standard scalar. This is a scalar from sklearn that will give each column in X mean 0 and univariance. So all of the columns will take on a similar range of values. Makes it easier for our model to learn. So x equals scalar dot fit transform x. Simple as that. Now if we look at x, we no longer have a data frame, but you can see the values have been scaled so that they all have mean 0, and most of the values lie in the -1 to 1 range. Okay, so now we'll split it horizontally or vertically. I don't know how you what you'd want to call it, but what I mean is let's get a train and test set. So x train x test, y train y test equals train test split xy. So this function from sklearn will just split our xy into a train and test set. We'll give a train size of 70%. Why don't I include a random state as well? How about 42? Alright, now we have 4 different sets for data, and we can begin modeling and training. So let's take a look at our feature data. So we have 20 features and 3,168 examples. I'm going to start building a TensorFlow neural network, just the most standard architecture, which is start with a dense layer, an input, and we'll pass in the shape of a single feature, single feature vector will be 20, a vector of length 20. So I can access that with x.shape sub1 and put the comma to indicate a vector. And x equals tf.keras.layers.dense. So this is a dense layer, we'll give it 64 activations and a ReLU activation function. Pass in inputs, then I'm going to copy that, make a second one, but pass in x. So it's going to go through 2 hidden layers, very standard, and then we'll give it an outputs, which will be another dense layer, but it will only output one value, which will be a probability estimate. So sigmoid scales are between 0 and 1, so that we get a probability for how likely a given person is male. Alright, we'll create our model, which will be tf.keras.model, and we pass in inputs and outputs. Alright, so let's take a look. We'll use model.summary to see how our shape is changing. We start off with a feature vector of length 20. It gets it goes to the dense layer, the first dense layer, which has 64 nodes, and then those 64 nodes get connected to the next 64 nodes, and those final 64 nodes all there's a linear combination that returns a single value from all 64. And that single value is, if it's over 0.5, we'll say it's male, and if it's under 0.5, we'll say female. So let's compile our model. So we'll give it an optimizer of atom. For loss, we'll give binary cross entropy. And metrics, how about we include accuracy and AUC. AUC is just much better at it considers performance within each class rather than just pure how well did we do across all examples. So we'll give that a name, AUC. Alright, then I'm going to fit the model and store the history of the fit in history. So model.fit. We're fitting on the train set, so x train and y train. We'll give it a validation split of 20%, a batch size of 32, and we'll train for 100 epochs. Because I choose such a high number of epochs because I'm also going to include a callback function. Just tf.keras.callbacks.early stopping. This allows us to monitor a value, in this case validation loss, and when we notice that the loss stops improving or stops decreasing, we will wait for a certain number of epochs, let's say 3, and if it's still not decreasing after 3 epochs, we're going to stop the training and restore the weights from the best epoch. So restore best weights equals true. Alright, we'll run that, and it should stop after some number, I think 9. Let's see how we did. Model.evaluate x-test, y-test. So we evaluate on the test set, we have an accuracy of 98% and an AUC of 0.99, so absolutely fantastic. Really couldn't hope for a better performance than this. Perhaps we could actually improve if we just tweak a few things, make it perfect, but I'm not going to spend too much time in this video doing that. I would like to actually try a different approach. Now, I do not expect, I'll just say this before I do it, I do not expect this approach to yield greater performance. This is absolutely fantastic. I have no reason to change this. If I were really caring about getting the best performing model, I'd probably keep something simple like this. But I want to try to use 2D CNNs just for fun, just to see if we can do this. And what I mean is, so a two-dimensional convolutional layer takes in an image, essentially, or a matrix of pixel data. It doesn't have to be pixel data, actually. It just has to be a two-dimensional matrix. And if you don't know the maths behind convolutional layers, you should go check them out. They're very cool. Basically, it just slides this little it takes data from the image, from little sections of the image. I'm not going to go into it in detail, but basically what we're going to do is we're going to reformat our sequences. Well, here, let me show you what I mean. Here's X, right? If I do it like as a data frame, we can just take a better look at it. The X is basically, each example is a sequence of values, of 20 values, right? And it's in a one-dimensional vector. Now, we could reshape this vector so that we can stack it into like a square, and then use that square as a two-dimensional image that we can feed into our convolutional network. I got this idea from someone on Kaggle was talking about how they got some interesting results using this in a competition. I can't remember exactly, but this is just an idea I had. Let's see how it goes. So how am I going to do this? So we have to work with X. X is our feature information, but currently it's in this format of just these long vectors. So each example is a vector of length 20. So what I want to think of is, if I wanted to make that into a square, I'm going to need it to be like, for example, it has to, the length of the original vector has to be a perfect square, and the next highest perfect square from 20 is 25. Obviously, if we need it to be of equal dimension for it to be a square. So if I look at the shape of X, currently it's of length 20, and what I can do is pad the sequences using tf.keras.preprocessing.sequence.pad sequences. And this function will take, let's pass in X, and we'll set a max length to 25. And I'm going to say padding equals post. What this will do is take all of our vectors of length 20 and add 5 zeros to the end of each one. So if I look at the shape of this, you can see it's the same, but there's 5 extra values at the end. And if I wanted to look at this as a data frame, so I'll take shape off the end, you can see, oh, very interesting. So I didn't know about this, actually. We're losing some information here. I had no idea. It turns them into integers, and that, we can't have that. Absolutely can't. So we're going to have to figure out how to avoid this. Is there a way? Let me look this up. Pad sequences. Is there a way to keep it from doing that? dtype. Oh yeah, let's specify dtype. Dtype equals numpy.float Okay, that's good. Alright, we're good to go. Awesome. So maybe I'll get some better performance than what I had before, because I didn't realize that it was stripping off the decimal values. Alright, so this is going to be, it's exactly the same as before, but we have these 5 extra zeros at the end. And the reason for adding those 5 is because now, let's just take this data frame view off. So let's make that the new x. So now x has these extra zeros at the end. We can reshape it now to keep the same number of elements in the first dimension, but change the other dimensions to be 5 by 5. And if you look at that, let's just get the shape of that. It is now, instead of 3168 by 25, the 25 has been restructured into 5 by 5 arrays. So, alright, let's see. There's one last thing. Usually, so let's make that the new x, take shape off. And then the last thing to do is, usually image data has an extra dimension to represent the number of color channels. So right now, the shape of x is 3168 by 5 by 5. I want to make it 3168 by 5 by 5 by 1. And to do that, I can use numpy.expand dimensions, expand dims on x, and the axis we want to expand across is 3, which will just be the 4th axis there. So run that, and now if we look at the shape, we have this extra dimension, and we have a nice image format. So let me just put these same block, and we have this, yeah. Okay, so let's actually take a look at these as images. So because they're in an image form, we can actually view them as images. So let's create a new matplotlib figure. Give it a fig size, I don't know, it could be anything. 12 by 12 sounds good. And then for I in range 9, so I'm just going to display 9 of the images. We're going to create a new subplot in a 3 by 3 grid, indexed by I plus 1. And then we'll use plt.image_show, or imshow, of x sub I. And that will give us the first image of size 5 by 5 by 1. Actually, I'm pretty sure we need to squeeze this. I think image_show doesn't like the extra 1. So let's do numpy.squeeze, just to get rid of that extra 1. We're still going to use it in the original x, but for the image_show function, we want to get rid of it. And then I'll just turn off the axis on the side, the axis marks. Alright, and then plt.show. And these are our new feature images. And you'll notice the line across the bottom is always 0. So we always have it as a solid color, because these are our padded zeros. So this is fantastic, right? What does it mean? So this is actually just a the brighter the color, the higher the value, I believe. Actually, so 0 is like this solid color, and then darker colors are negative, and brighter colors are positive. And so each one of these squares actually is represented. It's representing one of these values. So there's like 20 different values like this across, and each one of those is represented by a new square now. So it looks like colors to us, but to the algorithm, it's still just numerical data. So we'll be able to feed this into our model. Alright, so now we have a new x. Let's create a new xtrain xtest, ytrain ytest, train test split, xy, train size of 70%, and same random state as before, 42. Alright, and now let's build a new model. So before, our model looks like this, right? So just copy this down into here, and whoops. instead of using just two hidden layers like that, I'm going to use the standard CNN architecture, which is going to use a, we'll do a convolutional, so conv2d layer that takes the number of filters, which will make 16, and then size of a kernel, which will make 3, and an activation function, which will be ReLU. And this will take in inputs, and then we'll have a max pooling layer, max pooling 2D, and we'll pass in x to that. And so I'm going to copy this 3 times. Whoops. Make sure these are x, and this is going to be 32, and this will be 64. Then when we're done, we'll flatten it with a flatten layer, and we'll feed it through a final dense layer at the end. Alright, so let's see how this goes. We have a problem. Incompatible. Oh, I didn't pass anything in here. No, we're still getting a problem. Conv2d2 is incompatible with layer. Oh, I specified the wrong shape here. So no longer are we dealing with just a single vector. We need 3 values, 5 by 5 by 1. So shape would be 5 by 5 by 1, but I'll just represent it in terms of x.shape, x.shape sub 1, x.shape sub 2, and x.shape sub 3. Oh, what is this? Negative dimension. Oh, wait. Let me try just copying and pasting what I had before. Okay, give me 1 second. Okay, I figured out what I did wrong. I just had my kernel sizes were just way too big for the pooling that was going on. Our images are so small that we were trying to pool into negative dimensions. So don't worry about that. We're just going to keep it with 2 convolutional layers, kernel size of 2 here, kernel size of 1 here, and see how that works. So we're taking in this image and we're going to run it through the convolutional layer, max pooling layer, convolutional layer, max pooling layer. Then we'll flatten it out into a single vector, apply it through a last dense layer, and then give our output. So if we look at here, you can see the shape converges down to, it starts like this, sort of goes up a little, comes back down into 1. Alright, so let's now train. Okay, so I'm going to grab this code and put it over here. Just make sure everything's sort of similar. I don't think we have to change anything. It should be the same. Alright, I'll run that. And let's evaluate the model when we're done. And we actually get some pretty good results. So before, when we used just a standard way, we got a 98% accuracy and 0.997 AUC. Here, we actually have a higher AUC and a lower accuracy by only 3%, which is, that's pretty good. Like, this is higher than I got before, I guess because I didn't realize I was cutting out the float values here. I realize we may also be able to do this without padding the zeros on the bottom. I'm not sure if that will contribute, that will give us better results. We could just keep a rectangular image and instead of making it a perfect square, maybe a 4 by 5 image. But yeah, so I mean that's some pretty good results, especially considering how sort of like unconventional this method seems. It seems like this still wins, just a better performance. But I would love to look into this more and figure out if there is a way to make this more effective than the standard two hidden layer boring sequential model. But this is very cool. I hope you think it is also. This is going to wrap up today's video. Thank you so much for watching. I hope you enjoyed the video. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.